And can somebody just let me know that you're hearing me? How about first up on the list, Allison, you there?
Yes, we can
All
hear
right,
you.
you can hear me. Good. Okay. Hey, I don't normally do this. I apologize for pithy quotes early in the morning on a Wednesday, but this actually was a quote that was on the wall at my previous institution outside the math department. Mathematicians and physicists we kind of see things eye to eye, and I think Roger Bacon had it right on the mark here, and perhaps no more than in the study of magnetism. Unfortunately, if you saw what you had to read today and what we talked about on Monday, there's all kinds of stuff. There's being able to visualize in 3 dimensions because, like it or not, magnetism doesn't take place in the plane of your paper or my blackboard or whiteboard. It's a 3 dimensional phenomena. It just, you have to be able to see that. And being able to do a Rubik's cube is one of the more important skills in visualizing magnetism, mathematics. There's notation because you got vectors, and there's constants and units, the kind of normal things we see, but we're going to see calculus today too as well. All of those come together to be able to understand mathematics, and as Roger Bacon points out, if those are weak areas for you, okay, then it makes the learning of the science way more difficult. I often think about philosophically those biology folks who map the human genome from looking at diffraction patterns of X-ray, and looking at that film, and yet being able to interpret from what they were seeing on that film what the 3 dimensional shape of the human genome had to be. Phenomenal work, and I'm always awed by it because I've studied X-ray diffraction patterns for more regular things, cubic crystals, things like that. It's hard enough to figure out that in a 3 dimensional world, what the 3 dimensions correspond to in a diffraction pattern. The people are able to see that in 3 dimensions and map the human genome, I think, is an amazing accomplishment. Hey, I want to point out one other thing. I'm going to stop this share before I get started. I'm going to share with you Canvas, just because I'm going to make reference to something. Wow, I'm using Firefox for that. I don't normally use Firefox. Okay, hopefully you're seeing my Canvas screen. This is our home page, okay, for PHY112, Physics 2 here, all the way at the bottom in the module on magnetism. Of course, my PowerPoint that I'm going through right here today, the magnetic fields. And then right below it, I'm going to work out a problem of what the magnetic field is about a long wire. And of course, there's calculus involved. And as I talk about it, the calculus isn't as relevant as the result. Okay, the result might be something that a cynic would say is, oh, it's going to be on an equation sheet. I just pull up that result and use it. And you're not completely wrong with that. But, since a lot of you are taking integral calculus right now, it's kind of a 2-for-1 to see how do you do the integral that results in the magnetic field equation for a long straight wire. And at the end of the day, I would never make you derive that on any of the exams we've got left in the class, but there's a richness to seeing where that equation came from and what the assumptions behind it are. And any kind of mathematical model like that one, knowing the assumptions, knows when you can use the equation. And since integral calculus is something a lot of you are concurrently taking right now, I've worked out the entire solution in great detail. I used substitution. Actually, I used a trig substitution to do it. That's highlighted right here, and you'll see where I mean when I get to that point in the talk today. Okay, so I just want to show you where that is. There's my PowerPoint right there. There's the thing I'm going to be referring to. It's just me, my handwritten notes, working out a problem. It takes about a page. All right, I think we're ready to get going there, unless anybody has any questions. I see a number of you have started the lab. In fact, I think about a third of the people have already turned it in. I hope it wasn't too terrible. I mean, it got a lot better when my wife agreed to help me out, like Jimmy Fallon's wife does. She's a whole lot more. When I was trying to hold the camera and do the experiment, it was a little jittery and probably, if you could have given you a headache to watch. Once my wife helped me out, things steadied out, and I think the quality of the video is a whole lot better. I apologize for one time where you had to turn your head 90 degrees in order to read a reading. I didn't realize the iPhone was going to do that when I turned its orientation. That should be it. Let's get going. We're talking about these magnetic fields and what causes magnetic fields. And of course, the answer is moving charges, is what we talked about last time. And I did see a couple people turned in. Why is that here? Oh, because I'm sharing it with you. I want to stop the share, and I want to share with you PowerPoint. There we go. Fourth time here. I should be getting better at this. I can write better with my mouse, that's for sure. And I guess we're talking about the Biot-Savart law. Biot and Savart are the two French folks funded by Napoleon, as I think I mentioned last time, who worked in the field of magnetism in France. Napoleon believed that investing in science and technology and mathematics and natural philosophy and all those things, and discovery in the Nile and in the Egypt region, he believed that aided an economy, and then it aided the power of an economy and the power of a country as a result. In any event, we were talking about the comparison between calculating an electric field and calculating magnetic field, and there are some similarities. Both the fields decrease with distance from the thing that's causing it. In the case of an electric field, that's a charge. In the case of a magnetic field, it's a moving charge. They both have this constant, Coulomb's constant, or a magnetic like Coulomb's constant. I don't think our book ever introduces that anywhere, but you will see it. Instead, your book introduces the permeability of free space as opposed to the permittivity of free space. And one of the reasons why I've always liked physics is memorization was kind of a minimum. Understanding and knowing math and being able to do math are more important than memorizing. And so if that's your learning style, to not memorize but to learn to do things, you succeed better in physics, I think. And it worked for me. But if you notice these two equations and the permittivity of free space, for whatever reason, this constant has the permittivity of free space in the denominator when we're talking about electric fields, and it has the appropriate constant, the permeability of free space, roughly an equivalent for magnetic fields as opposed to electric fields, only the scientists who did the work in the day chose to put that constant in the numerator. And that's just one of those things you have to memorize, unfortunately. I didn't do it. It made me angry as a sophomore physics major when I'm like, these guys couldn't manage to make the equations look similar so that we can just see the pattern and learn that. But no, you have to remember that the scientists who worked, this is Gauss and Coulomb, they decided to put the permittivity of free space, epsilon zero, in the denominator with the 4 pi, and the Oersteds and Biots and Savarts and all those folks, Weber, they chose to put the constant in the numerator in their discipline, and they couldn't agree, and we haven't been able to fix it over the centuries that's elapsed since a lot of these people did the work. So you just have to remember that, and that's what takes the place right here. So if we found electric fields earlier in the semester as a constant over r squared, you're doing the same thing with the Biot-Savart law. The big difference here, is what I'm talking about with Roger Bacon's quote, the mathematics of this. Because a charge which is stationary, you have a coordinate system that just sits still. You don't need to worry about anything. It can be at a point and not move. But a moving charge doesn't sit still. It traces out some sort of line, some sort of curve. Okay. And the fact is, you got this sine of theta introduced right here. You could just say QV replaces Q, but you also have to remember the sine of theta. And I think back to, hopefully, sometime Professor Tech made you learn that a torque was equal to R, a radius, a moment arm, if you will, crossed with a force, first semester. And if you didn't learn it from him, I hope he covered it. He at least said those words. When you actually got down to calculating it, right, it was the magnitude of R, and our notation means that. Sometimes we just write the R without the vector or the magnitude symbols, the magnitude of the force, and then the sine of theta. And if that was okay for you to just calculate torques by taking R, F, and the sine of the angle, well, the same thing's going to happen here. That's what this is. This is charge times velocity times the sine of the angle in between them. And I would never try to figure out what the angle is without drawing the thing, drawing Q and V, a velocity V, and drawing what the vector R looks like, and actually deciding what is that angle. Okay. Now, the shorthand way of writing it, which is very succinct, is this, right? QV cross R is the same as Q times V times the sine of theta. The difference, of course, is that QV cross R has in its notation, in its mathematical conventions, the direction included. No problem with that. Okay. If you use QV sine of theta, you have to find the direction. And of course, what I'm referring to is the right-hand rule. The order matters. vector multiplication, cross product multiplication is not commutative. A cross B is exactly the opposite of B cross A. And if you don't have a method of doing this that has been working for you to do cross product multiplication, you want to either see a mathematician or see me real quick in office hours. But this picture is the answer. Fingers start in the direction of the first vector, swirl, or you point your middle finger or the rest of your fingers towards the second vector B in the order of operation of the multiplication, and then your thumb points to the result. And you just have to learn that. It's one of the things you have to learn to do vector multiplication. And people have variations of that, but it is your right hand, not your left hand. I always find it funny when I'm watching students do a test, and of course their pen is in their right hand, and so it might be natural to pick up your left hand to do this rule to figure out what the direction of a magnetic field or a torque is, depending on which semester it is. And you say you're using the wrong hand. You got to put your pen down if you're right-handed. Okay, so here's one of the times you lefties, the pen's in the right hand, so you can use your right hand. It was a choice. Somebody decided all this was going to be the right hand. It didn't have to be that way. It was just a choice, and it's a convention that we stay and we're consistent with. Of course, if you don't want to do it that way, okay, the first vector times the second vector times the sine of the angle in between them, this guy right here, you got to draw these first two vectors and look at that angle. And hopefully there's enough information in a problem that you're doing to let you figure it out. I'll give you a hint. It's often going to be 0 or 90 for us in our class. Okay. We're not going to make you often, or some easy angle like 30 degrees, you get the sine of 30 is just a half. Nothing going to be very difficult here. If you don't want to do it that way, okay, then there's this method we talked about before. It's on Monday, where you write out this determinant and evaluate the mathematical determinant. And it reminds you of all the 6 terms that are in the cross product that don't become 0 because a unit vector with itself is 0. Okay. Now, I should tell you, a ton of physics majors, a junior one time, refused to learn both methods. Okay. He said, look, I only need to know the first vector's magnitude, the second vector's magnitude, the sine of the angle in between them, and then I can always use the right-hand rule. And so I don't have to learn this thing that it allows you to do it by evaluating the components. He said, I can always find the magnitude of a vector. I know how to use Pythagoras' theorem to figure out what the magnitude of the hypotenuse of a right triangle is. And I'm like, okay, knock yourself out. You're not wrong. But there are problems where the easiest way to get the cross product is to do that. And there are times when the easiest way to do the problem is to take the magnitude of the two vectors, multiply them together, and multiply by the sine of theta and use the right-hand rule. The key is to know when to use which to make the problem as easy as you can for yourself. And to refuse to do one would be like not just saying in the language that you're learning, maybe even English, I'm never going to learn a synonym. I only need one word. I don't need both happy and glad. One will work. So why won't learn both methods? It's extra useless information. Then, of course, the moral of the story is a quiz came up or an exam or something like that. And there was a problem. And I didn't mean to pick it to make his method hard, but he spent a good 20 minutes doing the problem his way. Ultimately got it right because all he was going to do is get the magnitudes of these vectors, use the right-hand rule. And if he had been able to use the component method, literally 3 minutes, write it down, almost a trivial problem. And I didn't mean to make it hard on him. I didn't try to make that demonstration, but it sure worked out that way. Okay, a couple things about notation right here. What does this little thing mean over the vector? And the answer is it's a unit vector. And I wasn't perhaps clear about that. We had an example, I guess, where a charge was moving right there. And if you haven't looked at today's worksheet, that's it. So that's a little Q right there. And there's the charge. And it's moving along this line right here. Okay. And we're trying to find what the magnetic field is right there, which happens to be the origin of a coordinate system. And so the vector R here is the vector that points from the current location of the moving charge, okay, to where you're trying to find the magnetic field. And so, of course, that right there is the angle theta in that picture, okay? Now, what is this unit vector mean? Well, remember, whenever you get a unit vector, you take the vector. Oops, that's supposed to be a unit vector. Let me pull up my eraser tool. Sorry about that. And I'm slow to do this, but at least I know how now. All right, and so get the pen back. Yep. Pen, pen, come on, pen. There it is, pen. It's partly mouse clicking games. It is the vector divided by the magnitude of the vector. So what is the length of a unit vector? What's the magnitude of a unit vector? Much like asking when the War of 1812 is fought, right? 1812, what's the magnitude of a unit vector? Unity, 1. This has no numeric value. The only thing that piece does, other than make the equation look complicated, admittedly, and then Roger Bacon's quote comes into effect: mathematics is the key and the gate. The only thing that does is give you a direction. Cross R hat tells you to multiply by sine of theta. And more to the point, I guess, it tells you what the direction is using the right-hand rule or using the vector components. If you know that this thing is in the x direction, and R hat is both in the X and the Y direction, well, you can go to that determinant, fill in only the X direction for QV, and the R has a direction right here, both in the X, it has an X and a Y component, no Z component in this problem. Well, you can see that the only thing that's going to survive when you evaluate this determinant is that term right there. Okay, everything else is going to have a 0 in it because there's nothing. The AZ and the BZ in this thing are both 0. So the I and the J components will go to 0. And that's the kind of study and understanding you get from the determinant method. If you've never seen it, again, it's something that we can discuss at office hours. I'm sure your math professors would love to tell you all about cross product. They use it a lot. They use it because they needed it to describe things that happen in science, torques, magnetism. It's just a required part of the understanding. In any event, remember that has no contribution numerically because the magnitude of a unit vector is 1. So really you are just multiplying k times q times v over r squared. And I just want to make that clear because it's a common mistake. I see it all the time. You calculate r right here, which I think in this problem, it's a 3, 4, 5 triangle. So I think the magnitude is 5 here. Okay. That doesn't mean this is 5. The unit vector becomes 1, 5 over 5. Okay. In any event, I think that's an important thing. And then we asked the problem a second time because we let the charge move along its current path until it's right here. And now that does change R, doesn't it? See, this is the problem with magnetism that makes it more complicated than an electric field where I said the charge just stays still, right? QV, when it reaches this new location, where you're asked to find the problem, QV hasn't changed. It's still the magnitude of the charge and the speed of the charge. But you can see as the charge moves, R changes. So the thing down here in the denominator, the magnitude of R squared, it changes. And that does change. The other thing that changes, of course, is the angle is different. Over here it was some number, okay? And over here it becomes what I said will often be the case, 90 degrees, right? And so those are the two things you want to be careful with the worksheet, which is due at the end of the day today. And as always, I'll be in office hours. I think I like the 1 o'clock time for office hours. So you'll see an invitation for office hours if you have any questions on this. We'll talk about it then, 1 o'clock this afternoon. Okay, any questions anybody has right now before I move on to talk about a little bit more complicated situation, which is a charge moving in a wire? And the reason is because wires can bend. All right, well, the worksheet for today isn't that long. You just have to do this calculation twice and demonstrate some right-hand rule things. So let's move on. Yeah, we talked about units, and we'll talk about Biot-Savart law when the moving charge is in the wire. And so if you look, what's happened here are two things, I guess. I had to think of just a segment of the wire because I need a length and a current. And why is that? Well, let's just take a look at the units of Q times V. Q times V, that's units of charge, coulombs, unit of V, velocity, meters per second. And so I look at that and I go, okay, well, a coulomb per second, that's an amp and then a meter. So Q times V, coulomb per second, lump the coulomb and second together to be an amp times a meter, would be the same as a current times some length. And in some cases, you can just use length. Of course, the problem is when the wire starts to curve like this. We'll see what happens when we talk about a length, but even if the length stays straight, okay, the wire stays straight, if you notice, as I move from current in this part of the wire to current in this part of the wire, what we said happened with the moving charge, two things changed there. R changed and the angle theta changes, right? And when you get to a piece of current carrying wire right there, because the current's moving throughout the entire wire, R changes and the angle theta changes, doesn't it? And so that's why we write the Biot-Savart law when it's a moving charge in a wire. We write it as a differential. Okay, DS right here is the book's notation. Some other books you'll see DL if you look online or something. And then all we're finding is the contribution to the magnetic field from this little piece here, this little piece here, this little piece here. Of course, in integral calculus, we recognize there's an infinite number of those little pieces. And then the active integration causes us to add up those infinite contributions to the magnetic field. And of course, magnetic fields are vectors, so I got to add up the contribution to both the X component and the Y component of the magnetic field. Yep, Roger Bacon was right. Mathematics is the gate, because sometimes it locks people out, but it's also the key to mathematics, to understanding sciences, magnetism in particular. Okay, so that's the two variations, the two changes we've made to the Biot-Savart law from Monday. QV gets replaced by a current times a length. And the magnetic field isn't just a number of Tesla, it's a number of Teslas from that little bit of the wire that's carrying the moving charges. Okay, and so that's what we got. Permeability of free space is still the same constant. And so this K sub M right here is still the permeability of free space over 4 pi. This R hat unit vector can still be replaced by magnitude of I, magnitude of ds, sine of the angle in between them. And so this doesn't have any numeric contribution to the problem. It just reminds us to consider the sine of the angle theta. Angle theta where? The angle theta right here, between the direction of the moving charge and the direction to the point where I'm calculating the magnetic field. And hopefully in this particular case, you remember the thumb rule that we talked about, literally with your thumb, where you point your thumb in the direction of current on your right hand, you swirl your fingers around the wire, and hopefully you realize that symbol right there means the magnetic field from this little piece of wire down here is into the page, inward. Okay, and that's also one of the things that we're asking you on the worksheet that's due today. All right, so let's put it to practice. I have 3 problems I got to do. Cross product review is going to be important, as I said. You can do the component method. You can do the right hand rule method, using your right hand to figure out direction and just go magnitude of A, magnitude B, sine of theta to get the magnitude. But remember, a vector has 2 pieces you always got to figure out, both the magnitude and the direction. Whichever way you do it is completely up to you. Part of the art of doing science is figuring out which way you think is the easiest for a particular solution, particular such circumstance and situation, and getting to shortest way from point A to B. Having both in your tool bag, and it's like having 2 types of hammers maybe, or 2 types of wrenches in your tool bag, and you use the one that's going to work best for the job you got to do. All right, some things about the setup when you're doing a problem like this. Okay, the magnetic field is at some point, and that's the point that the vector R is being referred to here, whose magnitude is in the denominator and whose unit vector direction is sitting right there. The length of the current element is ds, and of course the wire has some I in it. So let's do what I think is a simple problem right here. Okay, and I've got this wire that's bent kind of like a coat hanger might be, where the segment comes in and the battery might be back here, right? That's driving the current. So there's a battery, and so I might have to connect this guy into some kind of loop. So that's what's not shown there. Current comes in right here. And I want to take the Biot-Savart law, dB, being equal to K sub n, mu0 over 4 pi, but I'm too lazy to write that, I times ds cross the unit vector that's pointing to the direction where I'm finding the magnetic field, okay, divided by r squared. And I want to break this up into 3 parts because I think I got different answers here. I'll call that segment A. Here, segment B, and then the third part. You may wonder why I'm doing it in that order. Hopefully here you'll see it in a second. Okay, so let's consider this segment A of this current carrying wire. And I want you to picture like a piece of the charge, or a charge moving, the current right there, okay? And I want to draw two vectors. Well, one of them I've already drawn, I times ds. And we're a little conflicted because I told you a while ago before the break, current's a scalar. Most people assign the direction to the length of the charge of the current carrying conductor, okay, ds, and we do it in the sense of the current, which is kind of double speak because I'm really saying it's the direction of current, and I'm thinking about I sort of like a vector, aren't I? I'm thinking about current as a vector. You can choose to visualize that and see that either way. As we pointed out, J, the current density, is a vector, but I, the scalar current, is not. I blame that on the electrical engineers who just didn't want to deal with vectors. In any event, so that's the direction of IDS, this term right here. And for this little piece of charge, R, I'm trying to find the magnetic field right there. So R would be that vector right there. And I guess the question is, what is the angle between IDS and R? And the answer is 0 degrees. Remember, this cross product with the unit vector reminds us to multiply by the sine of theta. And what's the sine of 0 degrees? Without going to your calculator, that's one that it is really handy just to know, because you know that the sine of 0 is 0. Picture a sine curve and it starts right at 0, doesn't it? And so what does that mean? All along this line right here, IDS cross R hat is 0. So the magnetic field from this piece of the wire, because it's causing current to move directly towards where I'm trying to find the magnetic field, 0. Okay, that's why hopefully you'll see the next piece I want to do is down here at B, where the current is moving that way. So that is the current ds vector right there. And R points from that piece of the current carrying wire to where I'm finding the magnetic field. And you'll notice those two vectors, well, the angle between them is 180 degrees, pi radians. And back to the cross product, this is the time where you want to use the sine of theta rule. Sine of 180 degrees, also 0. The magnetic field due to this piece of the wire right here is also 0. Pretty straightforward. If you got Biot-Savart law and you understand cross product, you understand the sine of theta is involved, you can visualize the two angles, 0 and 180 degrees, the current going in the direction towards where you're trying to figure out the magnetic field, the current receding away from the place where you want to find the magnetic field. Pretty straightforward. These two legs right here don't contribute to the magnetic field because they're right along the line where the magnetic field is being calculated. All right, so let's get to the meat of the matter, I guess. Let me erase all this. Any questions on that piece? Seeing and visualizing the cross product and why it is such an important part of this? All right, so let's get that out of the way. I probably should have kept my Biot-Savart law. We're going to do segment C there, the final segment, the curve segment, okay? And bring back my pen. And so magnetic field is equal to, and I guess I'm going to be able to write it as a vector here, and I think it'll be okay, is this mu 0 over 4 pi, which I'm too lazy to write, times the current in that little curved segment right there, okay, times ds, crossed with r hat, and divided r, there's a vector symbol there, that is an arrow, honest, over r squared. And you notice the book I stole this from, it's drawn two of those vectors for us, right? It's drawn ds, because ds is in the direction of the current moving that way through the wire because of the way I've drawn this little circuit right here, okay? R hat is drawn right there. R itself, in this particular problem, is the radius of that arc. And I'm just, I'm doing a very, very special case problem. I'm finding the magnetic field at the center of curvature of that piece of the arc, okay? So I guess this becomes pretty straightforward. It becomes, I'll write it out here, mu 0 over 4 pi just once, okay? Current's a constant. I guess I do have to leave ds right here, okay? And then I look and I go, cross R hat. Is there ever a place where the angle on a curved arc like that between DS, which is a segment of the arc, and R hat isn't 90 degrees? No, it's 90 degrees here too, right? Because that would be DS and that would be R hat, still 90 degrees. DS, R hat, unit vector pointing to the place where I'm trying to find the magnetic field. Sine of theta, sine of 90 degrees, 1, unity. Forget about it, okay? Just forget about it. And of course, R squared, also a constant for every piece because it's a curved arc. We call it capital R, that's why I circled that. It is the magnitude of the vector R before I divide through by R, okay? And so that's going right there. And I just have to integrate over the length. So that just means the length of that arc, right? That's a pretty easy integral to do. It just means the length of the arc. All right, well, let's see. We're given this angle theta, which is the angle which describes the arc. And I guess, let's see, arc length formula, again, one of those mathematical things you either picked up somewhere on the 9th or the 10th grade, or you didn't, but it was important for a lot of physics problems. It's just the radius of the circle that we're describing the arc on times the angle which is subtended. Okay, so that's what I mean by S. That is the answer to that integral. The integral of dx is x. The integral of ds is s. And we took care of the cross product when we decided that the sine of 90 degrees was 1. And so hopefully you can see the answer to this problem is just mu 0 times I times r times theta. And I'm dividing through by 4 pi and r squared. And it's the same r, capital R. So those two guys go away. And that's why I write this equation right here. The magnetic field is mu 0 times I times the angle which the arc is subtending, is being subtended by, I guess I should say, divided by 4 pi times the radius of the arc. Okay, now we've talked about the magnitude. We're good to go here, right? Because we use the cross product rule of magnitude of the first vector, magnitude of the second vector, sine of the angle between them. The question still remains, of course, what is the direction of the magnetic field right here? And it's two choices. You got to realize there's not an infinite number of choices involved in the right-hand rule. The only real question is, since the current is moving in the plane of the paper, the magnetic field's always perpendicular to that. So it's either into the paper or out of the paper. Those are your two choices. The right-hand rule is the thing that lets you discriminate between those two choices. It's binary. It's not an infinite number. So don't make it harder than it is. And the answer in this case, if you take the magnitude of the first vector that way, so you got to kind of point your finger downward, and then you point your finger, your rest of your fingers in the direction of the of our hat, okay? And hopefully you can see part of my hand here with my elbow up in the air. My thumb is pointing into the page, okay? And so this is an inward magnetic field with this magnitude, okay? Now, there's a shortcut. I notice it's not in our textbook, at least I couldn't find it. There is a rule that said, and it's kind of the opposite of this rule, because we said, hey, if there's a current carrying wire that way, we put our thumb in the direction of the current and our fingers wrap in the direction of the magnetic field. So my fingers would be coming out of the page here and going into the page down there. The symbol we use for that, right, is a dot here and a cross here. Okay, there's another right-hand rule that people use. In this particular case, if you let your fingers of your right hand swirl in the direction of the current in that arc, oddly, your thumb points right in the direction of the magnetic field. See how I'm doing that? And either way works. IS cross R is into the page, or you can swirl your fingers that way and it's still into the page. So again, I think there's about 3 right-hand rules that deal with magnetism, and you kind of got to keep them straight, because the question always is, what is the direction of the magnetic field? And that'll be even more critical next week when we go, okay, so if I put something right here, what's going to be the direction of the force on it, right? If you don't have the magnetic field direction right, you're going to figure out, you'll never be able to figure out what the direction of the force is. Oddly, it's going to be a cross product again. All right, now here's the one, the full math on this. is on that handout I pointed to, that one-page document on Canvas. But I do want to just straighten out that wire that was curved just a moment ago, and up the page it goes. And if you look at Biot-Savart law, the thing you've always got to figure out is this, okay? And as I pointed out, in this particular problem, R, not R hat, well, I guess R hat too because of the direction, and the angle are always changing as you move to different pieces of this current carrying wire, right? I think it's true that we know that the magnetic field is inward. And so I want to figure out what ds cross R hat is. And so I'm going to use this technique. You don't have to. You're still going to get the sine of theta, you see, but it does produce the inward magnetic field that we got from the right-hand rule. So I just wanted to show you how this works. ds right here is in the y direction, right? So there's no x component. There's no z component. There is only a y component, and I wrote it right there. A unit vector, like r hat, can be written as a sine of this angle and a cosine of this angle. Check it out. So if there's the unit vector right there, isn't its x component right there, which would be r hat times the sine of theta? R hat has magnitude 1, so it's just sine of theta. And right there, that's the y component, cosine of theta. So you take trigonometry and you put it right in this method of doing the cross product, and hopefully you can see the I component here has 2 zeros with it. The J component, also has 2 zeros, doesn't it? Okay. The K component, though, has this minus that. So 0 minus sine of theta dy multiplied by the unit vector k hat, because that's the piece right there that gives us the direction of ds cross r hat. So it's because it's 0 minus sine of theta dy, that's what we're going to use for this piece right up here. Okay, you could have arrived at that same conclusion with magnitude of the first vector, magnitude of the second vector, sine of the angle in between them, and you just got to make ds dy multiplied by the magnitude of a unit vector 1 times the sine of the angle in between them, and you could have used the right-hand rule to figure out this minus k right here, but I just want to show you an alternative method. All right, so that's what's going right up there, okay? Sine of theta dy and the direction, okay? And I guess then I had to just fill in the rest of the pieces of the Biot-Savart law, what I call the magnetic Coulomb's constant, mu0 over 4 pi. Again, I hate the fact that mu0 is in the numerator too, but we just live with it. I'll get over it someday, maybe not. And then r squared comes down, current I already said comes down. And so this is the thing I have to do. I have to integrate it, okay? And anytime you do an integral, you got to figure out what are my constants. Well, a unit vector is constant here, right? It's into the page. Mu0 constant, I, 4 pi. I didn't say the current was changing. 4 pi is definitely a constant. And I called this a long wire, and that's why I integrated from minus infinity to infinity. If you actually knew the dimensions of the wire, like it was 8 feet long, you might go from minus 4 feet to plus 4 feet. But this only is finding it at finding the magnetic field at the halfway point, isn't it? So again, this isn't a universal equation. This is an equation that works for a long wire, or a wire where you're finding the magnetic field symmetric about its length, right at the halfway point, okay, so that I can put in the right limits of integration. And we'll see why here in a second, I think. Do I have a slide of that picture? Now, maybe I don't. So come on, go back. It went too far. Okay, so I guess, now I don't have to worry about that, do I? I don't have to worry about that here. Next problem. So it's always, the magnetic field's always into the page. So I didn't have to worry about vector components here, really, did I? The magnetic field was always into the page. Good for me. The problem, of course, is as I integrate over values of y, the two things that I talked about early change. Sine of theta changes, because theta changes, and r squared changes. See, as I move, like I said before, that distance changes, that angle changes as I move to different pieces of the current carrying wire. I chose to use a trig substitution. And again, this is all detailed on that handout that I threw on Canvas. I used tangent of theta, allowed me to get y allowed me to get dy. And so for this guy right here, I'm substituting in that. I used the fact that the sine of theta, and yeah, I did pick minus y, didn't I? Because there's my origin. Y right now at the starting point where I'm evaluating is a negative number. And that kept my signs straight, okay, and allowed me to get dy, okay. And then I also needed to get r, so I looked and I said, well, the sine of that angle is big R over little r, and so I solve for little r right here as that. I jam that in right here, and a whole bunch of stuff canceled. That's the great news about a trig substitution. I've seen this problem done the other way, where you eliminate the sine of theta and get everything in terms of y. Perfectly acceptable. In fact, if you look at the example problem in our textbook, that's the way it's done there. I just wanted to show an alternative method, and I hope Professor Emerald will appreciate that I'm doing that for those of you who are in her class right now. You can always use a trigonometric substitution to solve an integral in this particular case, but you could substitute away y, you could substitute away theta, either way. But I like this because all of a sudden when I made those substitutions right there, constants, that r came out front, the capital R right here, the distance from the wire where I'm finding the magnetic field, and I was just left integrating sine of theta d theta. I think I actually have this wrong now that I think about it. This guy right here should be 0, because look at what theta would be if I was considering a piece of charge way down there. See how theta has gotten much smaller? And if I really went to infinity, this theta would go to 0. On the other hand, if I was way up at the top here, okay, that angle is going to be approaching 180. And so I wrote this backwards. I was thinking something different for a while. I have to just integrate from 0 to pi if I'm integrating over theta. Whereas if I was integrating over y for a very long wire, I went from negative infinity to positive infinity. And again, that's the beauty of a diagram. You got to be able to see that. And so you got to be able to draw it out. Well, hopefully everybody knows what's the integral of sine of theta. The answer is cosine of theta, right? Because, well, hold it. No, it's minus cosine of theta, isn't it? Yeah, integral of sine of theta is minus cosine. I hate sines and cosines because of that. The integral of cosine theta is the sine of theta. The integral of the sine of theta is minus the cosine of theta. The good news is, what's the cosine of pi? The answer is -1. What's the cosine of 0? 1. You subtract those two things, you get a -2, which cancels the minus sign out front, turns the 4 right here into a 2 because you have 2 over 4, and then all you have, those rest are constants. End of the day, there's my magnetic field equation for a long straight wire. Some distance r away from the wire. If it's a symmetric wire, I'll have to consider different angles or different lengths if it's not an infinite wire. Okay, so that's our equation, and we can use it, and we know the direction of the magnetic field because as we work through the problem, that's what we got. All right, one more to do, and then we're done here. Thumb rule again, okay? And I just, as a comparison, look at the electric field along a wire with stationary charge. The only reason I want to point this out is that Coulomb's constant, right? But doubled. This is twice Coulomb's constant. It is proportional to 1 over r, the magnetic field. So is the charge around a long straight wire, the electric field along a charged long straight wire, 1 over r. We've seen that before, right? There was a lab where you do an effect simulation where you showed for a long wire, fields go down as 1 over r, okay, for a long wire type thing. Whereas for a point charge, it goes over 1 over r squared. Same thing here. In place of charge per unit length, we have current, right? So a very similar equation to the electric field from a long straight wire. Direction is completely different, right? Electric fields are radially outward from the wire, and the magnetic field, you can see swirls around the wire like this right-hand rule is showing us. Last problem, magnetic fields due to a current loop, okay? The good news about this current loop, and just kind of think about a hula hoop maybe here, and this little thing right here means up at the top there, the current's coming out of the page at you, and then it swirls around this loop. We've only kind of drawn half of it. It is a full loop. It goes into the page there, and there must be a battery or something somewhere to drive the current around the circular loop. So if you're looking at it from your eye being over here, maybe, I guess what you'll be seeing there is current, and I guess it's coming around in a counterclockwise fashion if you're looking at it that way, right? So it's a full loop, and we're right out here along the symmetry axis. Again, we really haven't solved a lot of problems, right? We found the magnetic field around a semicircular arc when we're right at the center of the arc. Okay, when we do the long straight wire, it's either got to be an infinitely long wire, or we have to kind of be symmetric at the very center of the wire. And here, the only place we're able to find the magnetic field is along this what I call the x-axis. I think your textbook refers to that as the z-axis. Still draws it like I'm drawing it, and I'm like, why would you do that? Horizontal is x for everybody, so I changed that. Okay, so we're using ds cross r hat. Remember, this thing doesn't add a thing to us, right? It just gives us an angle that we have to consider, I guess. And let's see, the current right here is out of the page, and the magnetic field is being found right here. And I guess what's the angle between a vector coming out of the page and a vector that's in the page? And hopefully if you visualize that for just a second, you realize they're 90 degrees apart, right? If this vector r here, so r hat, because it's just a unit vector in the same direction, are in the plane of the page and the magnetic and the current is coming out of the page, they're 90 degrees apart. Again, the sign of 90 degrees is just 1. So I don't have to worry about it. So I wrote I ds cross r hat, this particular problem. It's just IDS. So that part of the vector problem is easier. Of course, the other side of it, though, is what is the direction of IDS? And so if you point your fingers, it's out of the page, and then you take your right-hand rule and you figure out how to cross that with r hat. See how my thumb is pointed up in this odd direction right here? That's the direction of the magnetic field from a piece of the wire with current in it at the very top. And if you think about it, as you consider pieces of the current carrying wire all around, what's going to happen to this magnetic field here is, I guess it's going to create, as you rotate around, this cone of magnetic fields that look like that. And so the magnetic field at any point can be anywhere on that cone. Well, that's kind of the good news, I guess, because if you look at the two components of the magnetic field anywhere along that cone, the perpendicular component cancels. There'll be another perpendicular component when you consider a piece of the wire down at the bottom, and those two guys will cancel. So all I need is this horizontal component, I'm calling it the X component right here, of the magnetic fields which are being traced out along that cone as you go along this circular loop. If you can't see that, office hours is a good time. We'll try to make that more clear with better diagrams. But that's the deal, okay? That's the deal. And so dB, the magnetic field from this little piece up at the top, this little piece right here, IDS, the magnetic field caused by that little piece right there is off in that direction. I think I have to get the component which is in the horizontal direction, and chose, because it's what most people do, that angle theta, or I'm sorry, that angle phi, which makes this angle right here 90 minus phi, which makes this phi, that's 90 minus phi, and there's phi back there. And so in order to get the horizontal component, I multiplied by the cosine of that angle phi. Okay, so that's what we did. And the good news, I suppose, once again, is constant, 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 r squared, r squared. Yeah, okay, the distance from there to there, anywhere along that loop is the same value, constant. The angle theta doesn't, or the angle phi doesn't change, constant. The only thing that's got to be integrated is ds. And so that's why I wrote this. All those things come outside the integral, and easy integral. Integral of ds is s. Okay, so but I did want to do a little bit better than r squared here, okay? This distance isn't something that is necessarily measured in the problem, but if you created a loop, the manufacturer of the loop would have to tell you what the radius of the loop is, and you decide how far away from the loop you want to figure the magnetic field. And so I substituted in x squared plus the radius of the loop for r squared. And then similarly, I guess the cosine of that angle, that would be the adjacent side over the hypotenuse. So the adjacent side is the radius of the loop. The hypotenuse is Pythagoras' theorem, x squared plus r squared raised to the 1/2. So that's what I put in for the cosine of theta. And then the last piece, I guess, is the integral of ds is just s. In this case, it's going around a full circle arc, so that means circumference. And so I wrote 2 times pi times r. Okay, put those all together then. Start canceling things if you can. Let's see. Start combining things if you can. I got U0. I got I. Let's see. I got R squared. R squared. I got 2 pi divided by 4 pi. So that's just 1/2. And then I guess x squared plus r squared, x squared plus r squared to the 1/2. There's really a 1 right here, right? So when I combine those two, I add that, and 1 plus 1/2, that's 3/2. And so this must be the equation to find the magnetic field of a loop anywhere along the axis of the loop. Now, one of the things you should hopefully have encountered in your life are things called electromagnets, solenoids. And what is a solenoid? Isn't it just a whole bunch of loops? And generally it's kind of coiled around like thread is on a spool. And if you have done the lab this week, you saw that the second exercise, part B, was to figure out the resistance of a long coil like that. Okay. And so we talked about the number of turns on the coil. And I don't know, I wrapped that one around as I was drawing maybe 5 times. And so what would you do to this magnetic field equation if you didn't have one loop, but if you had 5 loops or 10 loops or 1,000 loops, because the manufacturer really got kind of froggy and made a big, well, you multiply by the number of loops, because all the magnetic fields would still be in the same direction. Each loop would contribute this much magnetic field. Just, we tell you 3,200 turns, like I think we did in the lab, you multiply by 3,200, and that would be the magnetic field of a solenoid. And so it is a useful problem because people use electromagnets, people make solenoids, and this is how you calculate the magnetic field of the thing. What do you have to know? How big is the coil? What's the current in the coil? How far away from it along the axis are you in order to calculate the magnetic field? Everything else is just a constant. Hey, we'll come back on Friday. We'll talk about dipoles. That's all I got for you. I'm actually done on time today. Questions before we close up for the day? Okay, office hours to work problems will be on at 1 o'clock this afternoon. And of course, there is a worksheet associated with this one. What number are we up to? 25, I guess. And 25's worksheet will be due on Friday. And like I said, on Friday, we'll be talking about dipoles. And then another technique besides Biot-Savart's law to calculate not electric fields, magnetic fields around current carrying wires. You're going to find that this technique, this Ampere's law technique that you'll be introduced to on Friday, should remind you a little bit about Gauss's law for electric field. It is the closest analog to Gauss's law for magnetism. And until then, hopefully you have a good day. Enjoy your day off from physics tomorrow. But remember, if you haven't done the lab, that is due tomorrow, and I'll be around. I don't have office hours scheduled for tomorrow to talk about that lab, but if you have any questions, shoot me an email. I can set up a Zoom meeting to talk to you at office hours in just a second. Everybody have a great day, and I'll stop sharing this with you, and you can go ahead and move on to the rest of your day. I'm still 3 minutes over, aren't I? All right, stop the recording and break on out.